Okay. Good morning, everyone, again. In the interest of time, we'll get started. Um, First of all, welcome everyone to this a new semester and the new VCO series for this semester. Um, so my name is Anand Padmanabhan, and I'm a research associate professor in the Department of Geography and GI Science at the University of Illinois Urbana-Champaign. And I'm also serving as the managing director for iGuide, which is the Institute for Geospatial Understanding through an integrative discovery environment. And iGuide does various activities, including this VCOs that we regularly run almost on a weekly basis throughout the academic year and over the summer as well. So, welcome to this VCO series. Today, we have kind of a very interesting topic presented to us from one of our summer school teams, summer schools from last year. They were working on very interesting problem. We had a great time working in Boulder, Colorado, over last summer, and they are going to be talking to us about bridging the risk perceptions gaps around perception gaps around hazards. So this was a very interesting topic that we had a nice conversations and discussions at our summer school, and I'm sure the team has taken some of these forward and has learned quite a bit in that process, and they'll be sharing with us. And we'll also have another summer school this year. Again, that would be in actually this time it's going to be conducted in Minneapolis, Minnesota, in late July, I guess, or in mid-July, I should say. The call for that would be out soon as well. So any of the new students who might be attending, who might be interested in this year's summer school, you can see what last year's people have done and learn from that as well. So without further thing, I will pass on to Jennifer, our team lead, as well as the team, and to introduce the team and maybe to talk a little bit about the topic and pass it on to our students to get this done.
Thank you so much, Anand. Yeah, I'll pick it up here. I'm Jennifer Marlin. I'm a senior research scientist at the Yale School of the Environment and the executive director of the new Yale Center for Geospatial Solutions. And it is my complete pleasure to introduce the team from the iGuide Summer School. Just to give you a little bit of context about the work, we all know India is facing a rapidly intensifying set of climate-related risks, from extreme heat waves and drought to flooding to air pollution to energy disruptions that are all related. And often these hazards are happening all at once, and they're often happening in places with very high population density. And we have a lot of data, increasingly good data on exposure to these hazards. So the climate and weather variables and the land surface changes, but we know much less about how people are actually perceiving these risks and how those perceptions vary across individuals, across neighborhoods and communities, districts, and broader levels of geography. And so this gap matters because risk perceptions, or how people think about the risks and prepare for those risks, are ultimately going to drive real world outcomes. And yet there's not been a systematic way to sort of understand these variations and what people are thinking about the risks, even though that does connect to behavior. And so we have the exposure data, we have less of the perception data, and that's what the team is trying to, that's the gap that they're trying to bridge. So we built on national survey data collected by the Yale Program on Climate Change Communication, led by Tony Leiserowitz and Jagadish Thaker at the University of Queensland and others on the YPCCC staff. Many hours were spent collecting this individual level survey data that the team will talk about. And so the iGuide team combined individual level responses with climate exposure metrics and socio-demographic variables. They're going to talk about machine learning and AI-based modeling that they use to develop individual level predictions of perceived risk for multiple hazards. But then they took a critical next step, not just modeling how people think or perceive these hazards, but also generating district level maps of climate risk perception across the country, which is still ongoing. And so, what's especially impressive about this team's work is that it really sits at the intersection of physical science and climate science, but also social science and incorporating advanced geospatial methods. And it's not just the methods for the method's sake, it really is about producing insights, data-driven insights, scientific insights that are going to have meaningful implications for policy and decision making for practitioners who are trying to design emergency alert systems, for example, to help people get prepared. So you're going to hear from 5 different PhD students, and they're each contributing substantial components of the pipeline, from data integration and modeling to validation to interpretation, and they've together built something that is really technically rigorous and socially meaningful. And so I'm going to turn it over to the team actually to pick it up here, and they will introduce themselves briefly before they kick it off. So over to you, Deepika.
All right. So, hi everyone. My name is Deepika. Should I get started with the presentation?
Yeah.
Okay.
Yeah.
So we're team one of the iGuide Summer School 2025, and we're here today to present our work on flood and drought risk perception analysis for India. This is our team. That's Jen, who's just spoken, and there's myself, Deepika. There's also Surabhi, Amina, Pratyush, and Michael. And I will do this. Okay. So I'm going to set a little bit of context about why this is important in a country like India. Some of these risks really matter. What you see on the screen in front of you is satellite images of the village of Dharali in Uttarakhand in India before and after a flood that happened on 5th August 2025. Incidentally, this is when we were at the iGuide Summer School. So what happened was there was a flash flood, and there were massive torrents of water, mud, and boulders that completely obliterated infrastructure and claimed numerous lives. So this was essentially a cloudburst, and there was like intense localized rainfall of over 100 millimeters within just a span of a few hours. And there was landslides, and there was a rock and ice avalanche, and you can see that it's been completely wiped out. Uh, while experts have said that in 2025 there were more frequent episodes of intense rainfall events in this area, which is like a fragile Himalayan ecosystem. So this kind of tells you how important it is for people to be prepared with these risks, because the devastation can be truly horrifying. There's a cup. So like Jen likes to say, if you don't know that you're at risk, then you're more at risk. So there's a couple of reasons why it's important to see if there is a gap between formally assessed, sort of expert assessed risk and what is perceived by people. Because so if there is a gap, there could be like a couple of explanations. One is that people could be underinformed or not aware. And also, importantly, it could be that expert assessments are missing something crucial. They're missing crucial information, which is leading to the gap. So, in any case, it's kind of really important to know where the gap is and how much it is between what is assessed by experts and what people perceive. And that really is the motivation behind our project. So the objectives of our project are to estimate the percentage of adults who are worried. Like we model perceived risk about flooding and droughts using the survey data. And then we construct assessed flood and drought risk, and then we quantify the gaps. I will now hand it over to Amina to talk about the data.
Hi, thank you, Deepika. Hello, everyone. My name is Emine, and I am a second-year PhD student at the Department of Informatics at University of Illinois. Now I'm going to explain the data sets that we used, so we can start with the next slide. Yep, thank you. So first of all, I want to explain the survey data a little bit. The survey data set covers a wide range of disaster types, like famine or cyclones or severe storms. But the scope of this project, we have narrowed our focus specifically for drought and flood perceptions. And this matrix illustrates the state-level concerns across various disasters. To ensure the statistical reliability, we just filtered the data to include only states with more than 100 responses. At first glance, guided by the color intensity, we can see that drought generates higher levels of concern than flooding. For instance, if you look for the Jharkhand, if I spell this correctly, but Jharkhand state, the drought worry is amongst the highest, whereas the concern for flood is a little lower than the drought. So we can go with the next slide. Yep. So these maps display the weighted survey results representing the percentage of people varied at the district level. So you can notice that there are some gaps. There are some districts with insufficient sample sizes, which cannot be estimated directly from the survey data itself. Instead, this data gap is exactly why we are developing this model. We want to estimate the vary levels in these undersampled regions to see how the people perceive the risks. And looking at the spatial trends, we can see the district vary belt around the northern and western districts, and this flood perception aligns with the drought perceptions. And this two maps shows the risk metrics. For the one on the left, we have the flood map between the years 2000 and 2018, and on the right map shows the precipitation deficit maps. We can see the areas on the eastern part of India have the flood. And if you go to the next slide, we can see the potential assessed risk metrics. So this report is published by Department of Science and Technology, and we can see the same eastern part have a high risk for flood hazard indexes. And yes, please, next slide. Thank you. We have in the survey data, individual level data sets, they are the demographics of the survey data. So we can see in the gender distribution, we have nearly a 50-50 split. For the age distribution, we have primarily the 30 to 44 age demographics. For the caste distribution, we have around 80% of people coming from other castes, and 20% of people are from tribes or scheduled castes. And for the urban and rural distribution, most of the people are living in rural places, 66% of them, and 33% of them are living in urban places. And in the aggregate level predictors, we used several key environmental and socioeconomic predictors. One of them is average precipitation. We used 2024 precipitation and temperature averages because we picked this year specifically because we believe that people are more likely to report being worried if they have experienced extreme weather or rain in the immediate past. So we use the same data with the survey data was collected. And also we have the temperature data similar to precipitation. We used ERA 5 for 2024. And we have sentiments for the flood. We analyzed sentiments from news report because the media can amplify or downplay the perceived severity of hazards, and news coverage is a significant driver of public concerns. They can manipulate easily how people think. So the next data, the fourth data set is nighttime lights, average radiance. We use this data as a proxy for development because higher development levels often correlate with education and infrastructure, which can influence how a community perceives risk. And last but not least, we used Alpha Earth embeddings. So these satellite embeddings are coming from different data sources. Basically, Google research processed satellite images like multispectral images, SAR images, or some text data into 64 principal components. So these embeddings are digital fingerprints of districts. So instead of just looking at one thing like vegetation or building, these embeddings use Google's machine learning to compress thousands of data points from satellite imagery into 64 components. So we believe these embeddings can capture complex environmental features that traditional datasets might miss, which allows us to better model how people perceive their surroundings. And yeah, and now I will hand over to Shravi.
Thank you, Emina. Hi, everyone. I'm Suravi. I'm a PhD student at Colorado School of Mines. So, moving on to the model section, we fitted multiple machine learning models to understand what works best for this problem. For example, we used random forest, XGBoost, and logistic regression. Random forest and XGBoost, they are tree-based algorithms that allow us to capture complex nonlinear relationships in our data. And logistic regression, it provides a simple and interpretable baseline for our prediction. And using the combination of these three models help us to compare performance among these models and also figure out drivers behind all these predictions. Next slide, please. So for the data we used, so for the spatial data, we used a spatially stratified trend test split to prevent a nearby district from inflating the model performance. So for that, what we did was we overlaid a 250 by 250 grid, 250 by 250 kilometer grid across India and sampled districts so that the training and testing data are spatially balanced. Overall, 80% of the districts were used for training and 20% were held out as spatially unseen test data so that our evaluation reflects some true spatial generalization. Next slide, please. And we designed multiple modeling scenarios to understand the added value of different data sources in our models. So the first model, it uses only individual characteristics such as age, gender, is it urban or rural, is it like caste, districts, etc. And then in the second model, we incrementally added environmental variables, for example, maximum temperature, average precipitation, nighttime lights, flood and drought sentiments, historical flood and drought risks. And in the third model, we combine individual characteristics with alpha Earth embeddings. And in the fourth model, we combined all three of the models. And this stepwise approach helps isolate how much each data layer it contributes to predicting flood and drought perception. Next slide, please. So we evaluated model performance using multiple evaluation metrics. First is accuracy. Accuracy provides the overall measure of correctness in our prediction. Second is precision, which tells us how many of the predicted perception cases are actually correct. And recall shows how many of the true perception cases the model captures successfully. And then F1 score, it balances both precision and recall. For example, if the precision and recall are both uh, well, then F1 score, it goes closer to 1. So for F1 score to be good, accuracy and precision should be closer to 1. So the fourth metrics that we used was ROC AUC curve. So this curve, it compares how often the model correctly identifies an event versus how often it raises false alarms across all possible decision thresholds. So for example, a higher value closer to 1 means model does a better job of separating a flood or drought perception from non-perception. So here, all four of these metrics, it range between 0 and 1, with values closer to 1 indicating better performance. So pass on to Pratyush for results on flood.
Thank you, Survi. Hi all, my name is Pratyush Tripathi. I'm a PhD student at University of California, Santa Barbara, and I'll be going over the results section from floods. Let me first orient you with this chart. So the x-axis here shows different models that Survi just mentioned, which is random forest, gradient boosting trees, and logistic regression. The y-axis shows you the different values of different metrics, say accuracy, AUC, ROC, F1 score, and precision. And then each of the bar display whether which model we are looking at, say model 1, which was only base metrics, model 2, which had like climate variables, model 3 with alpha Earth embeddings, and model 4 with everything else combined. And what you would see here is that let's say looking at F1 score, which is a harmonic mean between precision and recall scores, you would see that the random forest has the highest accuracy in model 3 and 4, which are close to each other. And the jump that you see between model 2 and 3 in F1 score in random forest mainly comes from adding alpha Earth embeddings, and that goes back to um, some of the points mentioned earlier about why we really want to explore alpha Earth embeddings, because some of the unexplained characteristics about terrain, which we may not be explicitly capturing. It could be soil properties, it could be irrigation, it could be yields, any of that in some ways or via some compounding path impact how people perceive risk. Um, may be captured by alpha Earth embeddings, and that's really the idea behind adding those in the model. And as you can see in F1 score plot on the lower left, if you look at the random forest group, that one has the highest accuracy, and we all know random forest is one of the most robust and difficult baselines to beat even for sometimes for neural network models. So that's what we find, that random forest does a pretty good job. In the next slide, we will see what are the feature importance of some of these. Next slide, please. So what you see here is not directly the feature importance, but the coefficients that we derive from logistic regression for all 4 models. In the first model, you see that there is a heavy importance on whether the respondent is from urban area or not. The gender of the respondent is also heavily explaining the outcome variable. And then the second model, in which we add sentiment analysis, that proves to be the most important variable in explaining people's perception, which kind of goes hand in hand, because whatever people feel like, they often is they often like go on social media, talk about it, the news is all around it. And in fact, um, it's a cycle where not only people's perception are made by what they watch on news, but also they influence what is shown on news. So given how the TV industry, media industry works, they show what people are interested in more and more, so it's kind of spiral. So higher importance of district flood sentiment kind of explains that to some level. And then, of course, we see urban and gender in second and third most important variables in model 3. In model 2, in model 3, you would see here that this A47 and A31 correspond to like alpha Earth embedding bands of the 47th band, the band at 47th index and the band at 31st index. So the way we had extracted alpha Earth embeddings to subdistrict level is calculating the mean, calculating the median, and calculating the minimum and maximum values, and calculating the percentiles, second and 98. This was to really capture the distribution of alpha Earth embeddings in a given district, because otherwise these are 10 meter resolution pixels, and these are like vectors. So what metric would you take that captures what the alpha Earth embeddings are for that district? So that's why, to capture the distribution of alpha Earth embeddings in a given district, we take mean, median, minimum, maximum, percentile, second and 98th percentile. So in model 3 here, if you see, the moment we add alpha Earth embeddings to model 2, which then becomes model 3, suddenly all the variables from alpha Earth embeddings become important. Say, for instance, A47 is the most important band, followed by A31, A4, and so on. So all the other variables that we were looking at in model 1 and 2 suddenly were downgraded in importance. Similarly, in model 4, when we add everything combined, we see that alpha Earth embeddings still dominate in explaining the predictive power of the model. And this pattern we observe in logistic regression model. Let's quickly take a look at the gradient boosting model. Because what's interesting to see here is that we are using models that have very different decision boundaries. Say, for instance, a family of models is more like machine learning E models are gradient boosting trees and random forest. They have very different decision trees compared to a logistic regression that has a logit activation towards the end of it. And the errors that they optimize in the backend to fulfill the prediction task are also quite different. And that is why here in model 1, you will see that the district code now suddenly takes a lot of dominance in explaining where what is the perception of that respondent is, which intuitively, if you think about it, makes a lot of sense because this is not a spatially isolated phenomena that we are trying to map. The phenomena that we are trying to map has a very strong spatial correlation, spatial autocorrelation. And then here the gender and urban variables, which were higher in importance in previous model, those take a back step in here. We see a similar pattern in model 2 as well, where the district code basically, you can think of the district code variable as the district fixed effects, in which we are telling the model what district the respondent belongs to. And that's why the model is like blatantly learning that in certain districts, the perception, there's a strong relation between what district you are in versus what perception you have about a certain climate hazard. In model 3 also, even after adding alpha earth embeddings, we see that the district code appears to dominate. But the obvious pattern that we have seen in the previous one, which is adding alpha earth embedding, does lower the importance of other variables. You could see here as well in model 3. The moment alpha earth was added to the model, soon after district code, the most important variable was A13, followed by urban and gender, which are the characteristics of respondents. And then even in model 4, after like combining all the variables that we have, we still see that district code dominates in the among all the features that we were using for fitting our model. Next slide, please. Now, in the last slide, we see here feature importance of a random forest model. Here we see like interesting patterns, which is that in model 1, district code tends to dominate, and all the other variables have smaller, lesser importance. In model 2, we see a similar pattern where district code has a high weightage, but here you see that now different variables appear to have like explaining power in terms of model's ability to explain perception, because mean of temperature max and age were not the factors that we saw in the previous slide. Those were like urban and the gender of respondents, but here mean of temperature and age begin to like explain this. And what this really is saying is that what I briefly mentioned, the decision boundaries of different models are different. A random forest model versus a linear regression model, and also the error that they are trying to optimize in the backend could be very different. And rest assured that the models that we finally used underwent a grid search approach where we did hyperparameter tuning to be able to maximize the performance of the model on held out test set. So none of these models are like overfitting the training data. We did a regress grid search, hyperparameter tuning to find the right number of trees, the depth of trees, penalty term, and so on. In model 3 here in random forest, you see that now it's an interesting pattern, which is district code, which was dominating much of the feature importance in model 1 and 2. In model 3, that begins to fade, and suddenly the age of respondent now takes the highest importance in model 3, followed by whether the gender of the respondent and whether or not they are in urban area, which aligns strongly with what we found in the first linear regression, logistic regression model. And alpha earth embeddings here don't seem to explain too much. And in model 4, even when we add like everything, all the variables that we have, we see a very similar pattern. So consistently across all these models, we saw that A13, A42, and some of these bands are consistently showing up, which made us think that maybe some of these bands have physical characteristics that explain in some ways, or that relate in some ways, to floods in the area. So in the next slide, what we display here is bands A13, A27, and A55. So why these three? Because there are 64 different bands and we can only display 3 at a time as RGB. So this is what the alpha Earth embedding bands A13, A27, and A55 look like for the Indian subcontinent. And you see here that in the northern parts, you see a pink tone towards the what is called the Indo-Gangetic Plain, which is agriculturally active region. And then there's a lot of groundwater extraction. Towards the east of India, you would see in the next slide a zoomed in version, where you would see this is the Sundarban Delta, Bangladesh, then some of the Indian states like Bihar, West Bengal, the northeastern states here. So if you closely pay attention to this, and in the next graphic that overlays the flood extent, you see that there is something that these embeddings capture related to floods. Next transition, please. So comparing that flood extent with alpha Earth embeddings closely does make us think that there's something that these bands are capturing. But these are 1D vectors. These are not like meant for humans, like human interpretation. These are not meant for us to interpret them like a normalized difference vegetation index or any other indexes, or say things that we do with regular classical satellite images. Say, for instance, looking at different band combinations, the true color composition or the false color composition where vegetation is highlighted. We look at them and try to make sense out of it in a traditional remote sensing data. But these vectors are not meant for human interpretation. These are like made for computer models to make sense out of it. But this was just we trying to like force ourselves to try to interpret what are the bands that help us build a stronger model. So yeah, those were the results from floods, and now I'll hand it over to Michael.
Yeah, thank you, Pratish. My name is Okikiola Michael Egbele. I'm a PhD candidate at Washington State University. So I'll be talking on the results we got from the drought analysis. Next slide, please. So drought is also one of the major environmental challenges faced in India. And depending on your source, about 81 districts are under classified as very high risk drought location, and about 188 also with high drought risk. So in modeling the different drought perception, if you look at like earlier speaker mentioned, we combine different model combination and also tested 3 different models. So for the drought perception, random forest and gradient boosting, the machine learning model seems to have higher performance across different evaluation metrics, the accuracy, the F1 score, the precision. So they seem to have higher modeling capacity in predicting the drought perception. Next slide. Back a little. Yes, so here, zooming down to gradient boosting and choosing it as our most preferred model, I just wanted to talk about our baseline model, model 1, that contained only individual characteristics information in predicting drought, while our model 3 is the model with individual level characteristics, as well as the alpha head embeddings that Pratyush has talked about. So just looking at both models, they have similar performance across these different evaluation metrics. And this is just to reiterate that alpha head embeddings were also very relevant and significant in predicting this environmental challenge, even from human perspective. Next slide, please. So just to talk a little bit about the future importance for logistic regression. So I want to move your attention to our model 4. So model 4 contains all predictive or covariates that we use, that is the individual level characteristics, the district level information, environmental covariate, as well as the alpha height embeddings. But for model 4, alpha height embeddings is not showing up for logistic regression, but this is different if we move to the next slide for random forest and XG boost. So Pratyush has explained the district code being relevant in predicting flood. They were also relevant here in predicting drought perception. But zooming down again to model 4, here for our machine learning model SG boost, alpha height embedding is popped up, and which shows that there is, like Pratyush explained earlier, the way this model decides their model framework are different. And this is also similar for next slide, random forest. Yeah, so in model 4 for random forest as well, alpha height embeddings, AEE, were also significant in predicting drought perception. And this is different compared to flood result, where even for logistic regression, alpha height embeddings were part of the future importance. Next slide, please. Just to summarize findings from this study. So for our flood perception model, the best model scenario was model 3, that is a model that contains individual level characteristics such as age, gender, with alpha height embeddings, and random forests had the highest performance. While for drought, our baseline model, the model with just individual level characteristics performed slightly better, even though other different combined model combination also had good performance. And for the best model for drought analysis, SGBoost also had a very high performance accuracy across the different evaluation metrics. So for both flood and drought perception, machine learning model seems to be the best in predicting those. And depending on the model we are choosing, alpha height embeddings were also relevant. Next slide. So just as I was explaining, alpha height embeddings were significant in predicting both human perception of drought and also for flood in India. And one interesting cool thing about this project is that we've developed a modeling framework that can be adapted in any country and to also model other different hazards like cyclones and others. Next slide. So what we are currently working on, in fact, we've gone a little bit deeper into this. We are refining the model to develop the passive risk map, and then we'll finalize the assessed flood and drought risk map. And based on this tool, we'll quantify the gaps between human perception of drought and flood, and also based on expert-based assessment of drought and flood, and then we'll quantify the gaps between what experts have mapped and what humans their humans' perception about these two environmental hazards. And then we have 2 manuscripts in preparation, which will be detailing all the information about flood and drought risk in India. Next slide. So our script that we use is on the HiGAT platform, and also we have a data notebook as well as the data cards detailing information about the different variables, the covariates that we use in our modeling approach. They're also available online. Next slide, I think that should be all. Yeah, this is just to show our data cards for the variables we use. And thank you all for listening. We'll take any questions.
have a quick question. Thank you. This was very interesting. I guess what was the reason behind choosing flood and drought risk perceptions? Because I know we have a queue. Was that we have a few more? Was that the data John Marlin gave you, or did you think that was the most relevant data to analyze for India?
I can partly take that question, and then if someone wants to add. I actively work on like floods, both globally and in India as well, and I can like totally defend that floods in India are really a problem, especially in northern part of the country, where the population density is like way higher than say national average or like the population density in Western countries. And India also like is home to one of the highest flood exposed population, and we are talking about over 600 million people that are directly exposed to floods, and that's why floods become like the like default most important like variable that we want to look at. Um, the other thing is that in terms of we also wanted so the eventual objective of this is to do a gap between perceived risk and assessed risk, and I think floods are also easier to map or like track. The actual floods is easier to track compared to say something else, because now we have like all weather satellite data sets like Sentinel-1. There are so many flood products from NASA, from Europeans, and so on. So we wanted to work on something that is not only important, but also for which we can get the most, say, which is easier to quantify, and we could get like most reliable data. And floods was one of the obvious choices. And droughts go hand in hand with floods. So for starters, we kicked off with floods and droughts, even though the data that we have has a lot of other variables. We choose to start with floods and droughts. If anyone else has anything to add, please add. Yeah.
And on top of that, we also showed a report that was published as a part of Department of Science and Tech in India. So they have published like flood and drought assessed risk for India, state-wise, district-wise. So that also like later became a factor for us to like compare our perceived risk to the assessed risk. Anything more to add?
I have a related question for the team, which is why you all think the flood models are not performing as well as the drought models. I'm just curious what you all think.
I can quickly maybe try to answer that. I think the flood it has to do a lot with how floods are being mapped, especially in urban areas and rural areas, because in some of the models we saw that whether or not the respondent is from urban area has explainability in terms of predicting perception. I have known from my personal experience that a lot of these satellite based flood mapping tools and techniques do a bad job in urban areas because they cannot see through the buildings or in narrow streets, especially in like country like India, where streets are narrow and sometimes say covered by vegetation, or let's say Sentinel-1 has become quite popular in flood mapping. It does a great job in mapping floods in open areas. But if an area is covered by, say, trees, which could be flooded vegetation or forest, or let's say, especially urban areas, the way Sentinel-1 works is it's not like perpendicular to the surface of the earth. It looks at the earth from an angle. And when there are buildings, it's not able to like figure out where all flood waters are. And people are trying to combine elevation models with open area flood extent to try to estimate flood extent in urban areas. But I think right now we don't have a great estimate of like actual floods in urban areas, which is partly maybe seen in our perception results, but not really seen in our the assessed flood risk, I would say.
Any other questions?
just to follow up on that, and like I'm not an expert on environmental data. I'm an expert on survey data, but does this mean that there is better drought, like objective assessed drought risk data in India than flood? Is that what you're saying? And is that why the drought models are performing better?
I would try to answer that. I think when there is drought in India, the way cities experience drought and how the local authorities manage drought is very different from floods. For instance, let's say city of Bengaluru, if it faces a water shortage, the city administration pumps in water from 100 or 200 kilometers far away. It's possible, it's doable. Of course, like it's a challenging task, but still doable. So the end user, the only thing that they experience is maybe slightly increased water prices. Okay, when there is drought. But when there is flood, water, the flood waters are inside people's house. It's not something local authorities can easily like get rid of. So I think it has to do at some degree with how people like experience that phenomena. These are like very like two different things. So when there is drought, there's shortage of water, which people do something about it and like get around it. But when there are floods, it's complete chaos. There's nothing that is possible until the water drains out in a few months. So I think it has to do a lot with how people experience these two different types of disasters.
Yeah, and then to add to it, so we are using satellite data to map drought and flood. They also have different temporal scales. So maybe flood can be, I'm not an expert in flood. I think Pratush can attest to it. But I think we can map drought easily with Earth observation data compared to flood, because drought takes time compared to flood that in a day or two, the water might have receded. So I think mapping these using Earth observation data also poses a little challenge, and that might also explain why we see our model performing better in terms of flood, I mean drought compared to flood.
Thank you. I think those were great answers. And yeah, any further questions for our presenters? Maybe I have one. I guess I know there is challenges connecting or collecting these data sets and publishing it, I guess sharing them broadly. Um, and I know you guys helped publish some of these things on the iGuide platform, but it could not be completely shared because of restrictions and things like that. What do you think kind of is the way for other people to actually build on your work and kind of take some of the data? Is it like just reaching out to you guys and working, or is there a better mechanism for us to making this happen?
I think all the data is actually published.
Okay.
I think the district-wise data are there, so people could explore other models or make different comparisons. But yes, but for other, I mean, the flood and drought, I think, is what is there. But if people are interested in exploring other hazards, encourage them. They can email me, and we can talk about, for example, heat in India has not been modeled, and heat is a deadly risk. I think there would be challenges that are hazard specific. So for heat, I think a lot of people in India are worried about heat, and there's probably not a lot of spatial variation. So it would likely be very difficult to model that. But that doesn't mean it wouldn't be worthwhile to do it and to show where the gaps are, because the risk in the north is different than the risk in the south, and coastal versus inland, and so on. And there are, I think, 3 or 4 other hazards that data are being collected for. and the YPCCC is ongoing work in India and more future planned work. So yeah, I would say I encourage people to explore the data cards and the model that's available already, and then also reach out if there's something additional that people are interested in exploring. Yeah.
Thank you. Yeah, I found the notebook that was published, but I thought, I guess the notebook itself has the data inside of it, I guess, for this particular scenario and the data cards, right? Okay. Yeah, I'll share the link of the notebook, I think, on the iGuide platform, which this team has produced, so that others might be able to use it or at least explore. And team members, feel free to add anything else which I might have missed that might be there, which would be useful for people. Okay. Any further questions? If not, I guess I would once again want to thank our speakers today, and our team one here from the last year summer school. Again, great work and great sharing. We also have a bunch of other VCOs coming up, as I said. Like there is a list of VCOs there. Next week, we have actually another summer school participants presenting, the team 5 participants who are also incidentally doing mapping of floods, but it is in a different context, not in India, but it is again using geospatial data fusion and machine learning. So might be interesting follow up to the presentations today. So look forward to seeing you. I have the link there in the chat, so you can register, and the videos for this section will also be posted online. Yes. Okay. Anything else before we adjourn?
I would just like to say that it's been a real pleasure working with the team. iGuide did a fantastic job hosting the summer school and selecting the candidates, and it was a ton of fun. And I encourage anyone who's thinking about applying next summer to do it. It's worth it.
Yeah. We will have calls out pretty soon for
Okay.
both instructors and participants. So there is room for all levels of people to participate in the iGuide for summer school.
Thanks for your support, Anand.
Thank you. Okay. If nothing else, we'll adjourn today and hope to see you all maybe next week or on another VCO.
Thank you.
Bye.
Thank you. Bye, everyone.
Bye.